Hello everybody. So in this video we're going to prove a famous theorem in commutative algebra and algebraic geometry, namely we're going to prove Hilbert's Nullstellensatz. In particular we're going to prove one version of it, because in the literature people don't really find exactly one version. There are several things that go by the name Nullstellensatz. So the plan is to prove 5 of those. And yeah, so for those of you who don't really know what the Nullstellensatz is, one way to look at it is that it's sort of a tool. It's like the first tool one needs in algebraic geometry in order to build certain correspondences between algebraic stuff and geometric stuff. So this is not going to be exactly apparent from this version, but I think I am going to make some kind of remarks in the upcoming videos. At least I hope so. Okay, so let's start by looking at the first version, which is the one we see right here. So what does the theorem say? So we start with a non-zero finitely generated K algebra, and what we're going to prove is that if A is a field, if it happens that A is a field, then it follows that A is algebraic over K, which by definition means that every element of A satisfies some polynomial, some non-zero polynomial with coefficients in K. So, okay, so in order to prove this, we're going to use the famous normalization theorem, which I am not going to prove. I'm just going to state it, and in fact, I should probably... Yeah. Okay, so we start with the following lemma, which is, so this is referred to as Noether's normalization lemma or theorem, whatever you want to call it, but I'm not going to write it fully. So the lemma states the following, that so okay, we start again with A being a finitely generated K algebra, and I should note that I'm not making any kind of assumptions as far as my field K. So in particular, I don't assume that K is algebraically closed, right? So K is just an arbitrary field. So I start with a non-zero finitely generated K algebra. And the lemma says the following thing. So we have, it's true that there's an integer that it could also be 0, right? And elements t1, tn of A such that the K algebra homomorphism, I'm gonna name him, let's call this phi, going from this polynomial ring to A and setting these guys ti to small ti is in fact injective and finite. Okay, so first of all, I mean, okay, it's obvious, I mean, that this is, I mean, okay, so when I say that A is a finitely generated K algebra, then by definition, it means that A is coming equipped with a ring homomorphism, which goes from, I'm gonna call this psi, and it goes from K to A, right? And I said how I'm going to find this phi, but I didn't really say what's happening on the constant polynomials. But I'm just going to use this psi over here. In other words, we have that phi of lambda is by definition psi of lambda for every lambda in K. And in fact, this exactly definition is what makes this homomorphism a K algebra homomorphism. I mean, a certain diagram is commutative. Yeah, this is easy. Okay, so we all know what injective means. So let's recall let's recall the finiteness of a ring homomorphism. So being finite means two things, and I think that I'm only going to use the first one, but yeah, anyway. So it means that A, the ring A, is integral over this polynomial ring. Okay, that is, by definition, every element of alpha of A, every element alpha of A satisfies a polynomial equation with coefficients in this polynomial ring. So I want to make a small remark, which is not really, it's not that important, but I mean I should mention because it's bugging me. So the remark is that, so since A is a ring, and I also have this ring homomorphism phi, by definition this means that A is an algebra over this polynomial ring, right? So when I have, so if F is an element in this polynomial ring and alpha is an element in A, then by definition when I have F times alpha, this is just phi of F times alpha, which now makes sense because phi of F lives in A and alpha also lives in A, and A is a ring, right? So when I say that A is integral over this polynomial ring, then and every alpha satisfies a polynomial equation with coefficients here, well, I mean that when I multiply, things from here and here, what I really mean is this. Okay, so yeah, I am going to use this or something like that below. So yeah, okay. So that's the first thing. So this is the first property of a map of a ring homomorphism being finite. And now the second thing is that A is finitely generated as an algebra over the polynomial ring. Yeah. So yeah, I think these are all the things that I'm going to need as far as Noether's normalization theorem. And yeah, I'm not, as I said, I'm not going to prove it. If I remember correctly, its proof it's quite technical and a bit annoying. So yeah, I'm just going to avoid it. I'm just going to use it now. Okay, so before we move on to the next thing, which I probably should write. Yeah. So before we move on to the proof of the theorem, I actually need one more lemma, which I am going to prove. Okay, so I think it's a pretty standard lemma in the theory of integral ring homomorphism, but yeah, anyway, let's see what it says and let's try to prove it. So okay, we start with two integral domains, and we also assume that we have, let's say I have a phi, a ring homomorphism from A to B, such that phi is injective and integral. Right, so phi is a ring homomorphism, and I furthermore assume that it's injective and it's also integral. So the lemma says that A is a field if and only if B is a field. Okay, so let's see how the proof goes. So okay, I'm starting with this direction. So I assume that A is a field, and I want to prove that B is a field. So what I do, I mean that the strategy is pretty simple. So I just take an element B living in B, and I assume that this is not 0, and then I'm just going to find an inverse of this guy living inside B. Okay, so the first step is to consider the A subalgebra generated by this little b. Okay, so this is by definition the A subalgebra generated by B, and since B is an A algebra, right? This is, of course, this is a subset of B. So so first of all, the first so what we're trying to do, the idea is that we're going to use a little bit of linear algebra, right? Which means that I have to, first of all, to use my assumption that A is a field. And how am I going to use that? Well, I'm just going to observe that this A subalgebra is in fact an A vector space. It's a vector space over the field A, right? So in fact, I mean, okay, I'm just going to write it now that since this guy is generated by only one element, this automatically implies that it's going to be a finite dimensional vector space, A vector space, right? Okay, so the dimension is finite. Okay. Okay, so now I consider the following map. Okay. So I'm gonna call this map psi, and this is going to go from this A vector space to itself. And what's going to be? It's going to be by definition, this is multiplication by B. So it takes an element x and it maps it to B times x. Okay, and it's easy to see that this guy is in fact A-linear. Is an A-linear map of A vector spaces, right? And now we have the following simple observation, that I assume that B is in an integral domain, and now I claim that this implies, it's easy to see that this implies that psi is in fact injective. And this is really easy to see because so if I have an element x living in the kernel of psi, that means that B times x is going to be equal to 0. But as we already said, this is a subset of B, which means that this is simply an equation inside B, and since B is an integral domain, we must have either that B is equal to 0 or that x is equal to 0. But by assumption, B is not 0. So x has to be 0, which implies that the kernel of the map has to be the trivial one, which means that it's in fact equivalent to the fact that psi is injective, right? But now, since these things are A vector spaces, being injective implies that it's also surjective. In fact, this is an isomorphism of A vector spaces, right? So if I call the fact that this map is A-linear relation 1, then relation 1 simply implies that psi is surjective, right? And now let's call this relation 2, and what's the finishing argument is that, well, since this is the A subalgebra generated by B, this is also a ring, which means that it contains 1, right? So 1 is an element of this guy, and relation 2, I mean the surjectivity of psi implies that we can find a B prime living inside this guy over here, which is a subset of B, such that its image under psi, that is B prime times B, is equal to 1. But of course this implies that B has an inverse living inside B. So B is a field. Right, and this finishes one direction. So the other one is not, I think it's a bit, well, it's almost the same, but as far as difficulty at least. So okay, so this was one direction and not so hard, but okay. So in order to go to the other direction, so now we assume that B is a field, right? And let me just rewrite what we have. We have a ring homomorphism going from A to B, and I assume that this is injective and that it's also integral, right? And by the way, when I say that, I don't think I explained it, but when I say that a ring homomorphism is integral, I mean that B is integral over A, right? So by definition, every element of B satisfies a monic polynomial with coefficients in A. Okay, So I want to prove that A is a field, so I pretty much follow the exact same strategy as before. So let alpha be an element that lives in A that's not equal to 0. Okay, so now if you want to be a bit sloppy, well, what you can do is that since this phi is injective, we can identify A with the image of phi, right? Which means that I can identify alpha with phi of alpha, but I'm not going to make any kind of, I don't really want to do those identifications. I just want to write down the argument as it is. So okay, so what I do is I consider, let's just consider phi of alpha, right? Of course, this is an element of B, but let's assume for the moment that phi of alpha is in fact equal to 0, right? Since phi is injective, that would imply that alpha has to be 0, but this is just not the case. I assume that alpha is not 0, therefore phi of alpha cannot be 0, right? So it lives in here. But now I know, I assumed that B is a field, and therefore it makes sense to talk about this guy over here, the inverse of phi of alpha, which is going to be, of course, living inside B star. Okay, now it's time to use this assumption, the fact that phi is integral. And how do we do that? Well, we have an element that lives in B and phi is integral, therefore it's true that so this guy satisfies a monic polynomial equation with coefficients in A. So let me just write this immediately. Okay, and let me write down this equation. So this is going to look something like this. So we have phi of alpha to the power of -1, and this is going to be to the power of n, right? So, and let me just call this, okay, phi of alpha, right? It's going to look something like this, and the coefficients lie in A. But let me remind you the comment we made a bit earlier, which is the following, that so when I have since we have this ring homomorphism, B is an A algebra, and by definition, when I have an element of A, say this guy over here, and I multiply it with an element of B, what I really mean is phi of this element lying inside A times the element of B, right? So let me just, so by definition, this equation by definition is equivalent to the following. Is exactly this. It's just phi of Cn-1 times phi of alpha -1 to the power of n-1 plus phi of C0, and of course these are still elements of A. So now let me make some simplifications here on those powers, and so this is just going to be phi of alpha to the power of -n, and this is going to be the same, and this is going to be 1 minus n, and this is just going to be, okay. Now what I do is that I simply multiply this equation by phi of alpha to the power of n. So this now becomes 1, right? And this is going to be, well, this is not going to change, and this is going to become phi of alpha, right? Yeah. And this is equal to 0. Right, and now what I do is that I just move this, I move everything except 1. I just move it to the right hand side. But now I also notice the following, the following simple observation, that I have 1, which is of course equal to phi of 1, because I assume that all my ring homomorphisms just send 1 to 1, and this is going to be minus, and then I'm going to, since phi is a ring homomorphism, I can just put everything together in one big parenthesis. And also, since this n is greater or equal to 1, now I have the right to pass it inside the parentheses. something that I couldn't do before, right? If we just look at phi of alpha to the power of minus 1, I can't just, this is not equal to phi of alpha to the power of minus 1, bringing the minus 1 inside the parentheses, because the simple alpha to the power of minus 1 just doesn't make any sense. Okay, so this is just minus, and I'm going to copy these things. Right, oh, forgot, so there's a C0 here, yes. And now, since phi is injective, I'm using that again. Well, this implies that 1 has to be equal to minus the guy living inside this parenthesis, so it's just so it's this thing over here. And now, well, of course, this is just so we just take alpha, we take alpha out, and this is just alpha times minus C0 alpha and minus 1, right? And well, since the coefficients here lived in A and the alpha also lived in A, this is just an element of alpha, everything inside this parenthesis. And also notice that n cannot be equal to 0, otherwise this equation wouldn't really make any sense. Okay, which means that this is at least 0, n minus 1, I mean, right? And of course, so we find an element in A such that I multiply it with alpha and I get 1. Well, this implies that alpha has an inverse living inside A, which of course implies that A is a field. Right, and this finishes. I think this finishes the proof of the lemma, and now we can move to our last theorem, which I think I have somewhere. Yeah. So this is Hilbert's Nullstellensatz version number 1. And the proof is actually very, very short. It doesn't really, it's really short. So what I do is that, well, since I start with a finitely generated K algebra, I can immediately use Noether's lemma, which means that, so we use Noether's normalization lemma, which implies that, let me just rewrite it, there is an n which could also be 0, right? And some elements in A, such that we have a K algebra homomorphism going from this polynomial ring to A, and this guy just sends Tj to small tj, and phi is two things: is finite and injective, right? So this is what the lemma says. I mean, Noether's lemma. And so, okay, so now we do the following. So if we look back at our previous lemma, which I'm not really going to show again, so we have a map. So if you remember, the previous lemma had to do with a ring homomorphism going from between two integral domains, right? So in our assumption, we have that A is a field, which of course implies that A is an integral domain. Of course, this is an integral domain, right? And also we have that our map is injective and that our map is finite, which means that one of the things that this means is that A is integral over this polynomial ring. So this gives us the right to apply the previous lemma we just proved. I'm just going to write it as lemma, and this implies that that A is a field if and only if the polynomial ring is a field, right? And of course this is true because we assumed it, and therefore what we really get is that the polynomial ring is a field. But this simply cannot happen if n is greater or equal to 1, right? Simply, I mean, if you just look at T1, I mean, if this was a field, then, you know, the inverse is 1 over T1, but this is not an element, this is not a polynomial. Therefore, if this is a field, the only possible case for this to happen is that n is equal to 0, right? this implies that n has to be equal to 0. But if n is equal to 0, then this is simply just k, right? And being finite means that a is integral over the polynomial ring, but now the polynomial ring just became k, right? But since a is by assumption a field, saying that a is integral over k is exactly the same thing as saying that a is algebraic over k, right? So a is algebraic over k, and this finishes the proof of the first version of Hilbert's Nullstellensatz.